Everything from the smartphone in your pocket to the massive power grid that lights up our world, it all runs on unbelievably complex electronics. But here's the thing, how do you test this stuff? That's the real challenge. It's a quest for the perfect simulation, a way to test these systems perfectly long before they ever touch the real world.
Think about it. It's a really serious question. How do you push the control system for a new electric car to its absolute limit without, crashing an actual car? Or how do you fine-tune a city smart grid without the terrifying risk of causing a massive blackout? The answer is you have to build a virtual world so convincing, so realistic, that the hardware you're testing doesn't even know it's not real.
So the way the industry usually handles this is with a technique called hardware in the loop, or HIL for short. The idea is actually pretty cool. You take the real brain of the system, that's the controller, and you hook it up to a powerful computer that simulates everything else around it. The controller literally thinks it's managing a real power grid or a real electric motor, which means engineers can throw any crazy scenario at it, all in complete safety. But the standard approach, it creates a huge problem. And that problem is what we can call the simulation trilemma. Basically, engineers are forced into an impossible choice. You can have your simulation be fast and accurate, but it's going to be incredibly expensive. We're talking about needing specialized programmable chips called FPGAs that can cost a fortune. Okay, so what about fast and cheap? Well, then you're sacrificing accuracy. And accurate and cheap? Forget about it. It's just painfully slow. For decades, you could pick two, but you could never have all three. So why are these old methods so clunky? Well, it all comes down to their brute force approach. It's called fixed step. The simulator just chops time into millions of tiny identical slices, and it runs a full calculation on every single slice, even if absolutely nothing is happening. It's like setting a camera to take a million photos of a statue. Almost all that effort, all that computing power, is completely wasted on nothing. And that leads to the big aha moment. The simple question that changes everything. What if, instead of that brute force method, you could build a smarter system? A system that just ignores the empty space and only computes the stuff that actually matters. This is where event-driven simulation comes in. And the core idea is just brilliant. The simulation totally ignores all the quiet periods and just jumps from one critical moment or event to the next. The only time it does any work is when something actually changes, like a power switch flipping on. This means it can take these huge leaps forward in time when the system is stable, making it way more efficient. Just look at the difference. It's dramatic. Instead of thousands of those tiny, wasteful steps, the new timeline just hops from one important event to the next. The number of calculations gets slashed because we're not wasting our time on the quiet moments. It is so much more efficient. But, it does raise a pretty big question, right? For this whole thing to work, the simulator can't just react to an event after it happens. That would introduce delays and inaccuracies, which defeats the whole purpose. It needs a crystal ball. It needs to know the future, to predict exactly when that next switch is going to flip. How on earth do you do that? Well, the answer is this amazing technique called switch event oversampling, or SEO. This is really the secret sauce. Instead of just sampling the controller's signal at a normal speed, the simulator oversamples it at a ridiculously high frequency. By analyzing that signal pattern in just the first half of a single control cycle, it can perfectly predict every single switching event that's going to happen in the second half of the cycle, well before they actually occur. It's kind of like watching the first 10 minutes of a movie and knowing exactly how the whole thing's going to end. Okay, let's break that down. Step 1. The simulator and the controller sync their clocks, so they're moving in perfect time. Step 2, the prediction. It uses all that oversampled data from the first half of the cycle to calculate the exact future timestamp of every event. And then step 3, the correction. It keeps oversampling in the second half, not to predict, but just to double-check that its predictions were spot on. This completely gets rid of the delay that plagues older methods, giving you perfect accuracy. So, okay, we've got speed and we've got accuracy. But what about sheer size and complexity?
It's one thing to simulate a single little component. But what if you need to model something enormous, like a full-scale smart grid or the entire power system of an electric ship with hundreds of interconnected parts? Trying to solve that whole system at once becomes a computational nightmare, even for this smart event-driven model.
So, the next piece of the puzzle is called parallel acceleration and circuit partitioning, or PAC, and it's a classic divide and conquer approach. The researchers figured out a way to take a massive complex circuit and computationally slice it into smaller, more manageable chunks. Then, each of those chunks is solved at the exact same time, each on a different core of a totally standard off-the-shelf multi-core CPU.
But here's the catch. When you chop up a circuit like that, you run a huge risk of introducing errors. If the calculations for each piece aren't perfectly aligned and stitched back together, you get what the researchers call simulation distortion. It's like you've cut up a puzzle, but the pieces don't quite fit back together anymore. The whole simulation becomes unstable and useless. So the key was figuring out how to divide the system without breaking it.
And the solution they found is just so elegant. They figured out that you can split the circuit at very specific points, at the parts that store energy, like capacitors and inductors. Then, and this is the magic, they used some really clever math, specifically high-order derivatives, to precisely calculate the interactions between all the separate chunks. This clever math acts like a perfect glue, guaranteeing that even though the pieces are being solved on different CPU cores, they fit back together seamlessly. The result? Absolutely no distortion. No errors, just a mathematically perfect picture. Okay, let's recap. We have an event-driven model to be fast, we have a predictive sampling method to be super accurate, and we have a parallel processing strategy to handle massive scale. So the big question is, did it all actually work? Did they finally break the simulation trilemma? Oh yes, and the results are absolutely staggering. When they tested this new method against a top-of-the-line commercial simulator, it was 42 times more accurate. Let me say that again. That's not a 42% improvement. That's a 42-fold leap in precision. It's just a completely different league. And it didn't stop there. This new method could handle simulating systems that were 3 times larger than what the expensive, specialized FPGA simulator could manage. And remember, it was doing all of this on a regular desktop PC.
And that brings us to the cost. Remember that trilemma? The one that said you couldn't have fast, accurate, and cheap? Well, this new method delivered all that world-class performance for just 1/16 the hardware cost of the commercial FPGA system. It didn't just bend the rules of that old trade-off, it completely shattered them.
And finally, of course, speed. When compared to other modern algorithms running on the same kind of CPU, this new approach was between 3 and 10 times faster. It's just a total, comprehensive win across every single metric: accuracy, scale, cost, and speed.
So, what's the bottom line here? Why does all this techie stuff matter to us? Well, it means engineers can now design, test, and validate new technologies way faster and cheaper than before. It means we can build safer EV charging systems, more reliable smart grids, and figure out the best ways to integrate renewable energy. It basically takes ultra-high fidelity simulation, something once locked away in expensive labs, and makes it accessible to pretty much anyone with a decent computer.
This is a true revolution in how we can innovate safely. It opens up so many new doors. And it leaves us with one last really exciting question to think about. Now that we can build a nearly perfect virtual testing ground, what technologies that seem impossible today could we finally bring to life tomorrow?